3 in a row today.
Maybe sometime next week.
We had 5 yesterday. Or 4 yesterday. 3 in a row today. Okay.
Guys, make it short. Make it short, yeah? All right. Make it as short as we can. Just I get it. Yeah. We'll do it. You get them out?
All right, welcome everybody. We are team number 3 for ECE and 21 for ME. We're the Formula Electric team. We have slide numbers. If you could please save all questions till the end, just because it's a long presentation. And I'm George Simic.
I'm Scott Hill.
Sam Risberg, Steve Pinsky, Corey Snow, and Danny Covio.
And I'll hand it over to Danny.
I'm just going to close this really quick. Okay, my name is Danny Covio. I'm going to go over the top-level electrical system as well as some of our test plans that we're planning and what we've done so far. This is our electrical schematic. It's very similar to what you saw last time. I have taken some things out. We've really tried to simplify the system. One thing that is missing on here that I took out that we actually found a speedometer, Scott Hill and I, and that actually has been tested. And so we will be implementing that. There are opto-isolator circuits here and there. The speedometer doesn't require one because it's only connected to the low voltage system. Okay. This is our Agni 95R motor. This is just, again, data from the manufacturer. We are going to test it ourselves, although probably not in this much detail. It's very popular among other Formula Hybrid teams, and if our performance is anywhere near what this leads us to believe, then we'll be very happy. This is also our motor controller. One thing about this controller is that it is not optically isolated, so that's very, the competition requires that things like anything that enters the cabin, like your pot box, your throttle potentiometer, or brake potentiometer, and all of your master switches and things like that that affect the ground fault detector have to be isolated. And for our motor and controller testing, we're trying to verify that the motor actually in fact runs. We're going to attach it to the controller, run it at about 72 volts DC, and make sure that it spins in both the forward and reverse directions and accelerates as a function of the potentiometer value. The status so far, I've had some difficulty programming the controller. We haven't found a powerful enough DC power supply yet. The controller requires a minimum of about 24 volts DC.
And can provide the power supply.
Correct. And we've only had a 24 volt DC power supply up in the senior design lab, and it doesn't like that. So it constantly resets and can't connect to the computer. So our solution right now is to hook it up to about an 80 volt DC power supply so that it's simulating a fully charged battery, and then retest that and see if that should eliminate the low voltage error, and we're hoping the frequent resetting error.
Do we have say 100 volts DC power supply and I think
Dr. Harvey has a DC
Yeah.
power supply that we can use,
150
and
volts
if that doesn't work, we have some lead acid batteries already that we can use to actually test this and just put them in series to test the correct voltage. If we have any further problems with the controller, I have 2 contingency plans here. I contacted Kelly Controllers, and they have 2 controllers. The first one is almost an exact replacement for our current controller, except that it's optically isolated. It has the same voltage range and the same current range and still has regenerative braking, and it's about $600. The second controller they recommended to me because it would offer us more flexibility in terms of voltage and power, and would also be advantageous to future teams if they wanted to bump up the motor to a more powerful design, and it's about $1,000. And both of these controllers would eliminate the need for the optical isolation because they both have it built in. As for the opto-isolator circuit, I showed you about this portion right here last time, and all I've added is the 5 volt regulator and the 5K potentiometer on the left. And basically the objective here during testing is that, or what we'll do is attach a 5 volt DC power supply where the regulator is, and actuate the throttle and see if the output voltage corresponds directly to the input voltage using a voltmeter.
But how you provide this 5 volts power supply in the car? I know you can test
Oh,
it
in the
your
car?
lab.
Oh, we
Yeah.
have a low voltage battery that we use. It's about 12 volts, and then we'll use a 7805 voltage regulator to limit it down and just hold it at 5 volts. It'll burn off the extra 7 volts, which is somewhat inefficient, but that shouldn't be a problem for our design. And we want a very steady 5-volt source, and that's how we'll actually use it in the car itself. And let me see. And the input and output voltages should correspond linearly. And also the output voltage actually only needs to be between 1 and 4 volts. Anything below 1 or above 5, the controller just kind of throws out. If it's above 4, it thinks it's fully open throttle, and if it's below 1, then it thinks it's fully off. As for the speedometer testing, I have a video actually on the bottom there. And this is a Autometer 4480 speedometer. It's from one of the previous year's teams. And it requires a, basically it actually has a lot of different inputs. You can use a Hall effect sensor or PWM, whatever you want almost to control this, and it just counts the pulses. And it can be calibrated to anywhere between 500 and 24,500 pulses per mile. And you just calibrate it over a 2-mile period. So I simulated a pulse with a sine wave generator, and then I calibrated the speedometer and made sure that it actually corresponded to the frequency. And hopefully you just caught that video that it showed that it does in fact work. And we're going to buy a Hall effect sensor and wire that into the car. And again, this doesn't require optical isolation because it's only connected to the low voltage source. As for the pop-X testing, this is very simple. We'll just hook it up to a 5-volt power supply and measure the output, the wiper, and it should basically just correspond just like a voltage divider and give you somewhere between 0 and 5 volts depending on where it's located. So very simple there. And now I'm going to pass this over to Scott Hill to talk about the battery system.
I'm going to talk about the battery system and the BMS. There's been some pretty significant changes as far as the batteries go due to issues with getting the batteries. Right here I'm going to talk about them. This is kind of the process we went through trying to get the lithium polymer batteries, and the reason we're having to change the design. The first one is because we tried to contact the company Hobby King, who we found the best price for batteries through. They didn't take purchase orders. We tried multiple times to contact through them. The second one is we checked with the local hobby store to see if they could order it for us, and they said they could. They quoted us a price originally, and then once we finally got the estimate for it, they jacked up the price by about 20%. So we rejected that offer because it wasn't what they had told us originally. The last thing that we tried is 2 of the members on the team were going to front the money and be reimbursed through the school. And by the time we had got to this stage in the process, the batteries went backwards through the company. And we contacted the company. They said they would take about a month for them to be in stock, and they'd still have to ship to China from us, from China to us. So with the time constraints we were given, it wasn't a feasible option. And at this later point in the process, we had to find an alternative. Yeah, they just talked about what I was saying. Some of the alternative places we looked through to order the batteries were 4Acre Electronics and Battery Source. Unfortunately, the only 2 kinds of batteries that those companies could order were nickel metal hydride and lead acid batteries. So we took a look at our options through that. After looking at those, we found that they had a certain type of lead acid called the high discharge series, which, while not quite as good as the lithium polymers, it definitely was within the range of what we wanted to do. I'll explain the characteristics a little bit more on the next page. But some of the pros and cons of the 2 different battery types are shown here. Of course, the lead acid batteries are less expensive, but they weigh a lot more, so that's an issue there. And with the nickel metal hydride, we would need a lot more batteries, about twice as many as with the lithium polymer. So taking that into account, we decided to go with the high discharge lead acid. With those, there's a significant increase in weight, so we reran our power requirement simulation to make sure that we would have enough power to complete what we needed to. From that, we decided to go to a 36 amp hour battery instead of 30 amp hour. These are the characteristics of the battery we've chosen. As you can see, the weight is significantly more, 26.6 pounds apiece, but we only need 6 of those versus 120 with the lithium polymer. And you can see a comparison of the different characteristics down on the bottom. Of course, the lead acid has about half the discharge of the lithium polymer, but it's still a significant amount so that we can compete. And then list the price per battery down on the bottom. As far as the BMS changes go, due to a different type of battery in there, the contest requires different measurements in our battery management system. Since we're going with the lead acid, it no longer requires us to measure the voltage per cell, so that significantly decreases the complexity of the BMS. However, we do need to measure the temperature of each cell to make sure that they're not overheating, which I'll discuss on the next page here. This here is our new battery system and BMS schematic. As you can see, the batteries on here are represented, and we also represented the internal resistance of the batteries, which is about 13 milliohms. We have the fuses on here, which are rated at 400 amps, because due to the competition rules, we had to have fuses that were a certain percentage above what they could actually output. And then in here as well, these black circles are temperature sensors, where we'll have a low voltage circuit connected to that to power them. And then there will be a logic circuit that will be connected to a relay in the middle, so that if the temperature gets too high, it'll shut the relay off and shut down the battery system. This here is the ground fault detection circuit. It'll basically make sure that if there's a short between the high voltage and the low voltage circuits, it'll shut the system off so that nobody gets electrocuted. It operates from 0 volts all the way to 800 volts, so it's well within our range. And then this here is the schematic for the ground fault detection connections. As you can see there, where we have the high voltage DC bus, and then we'll connect that to the isolator. And then we'll have these connections on the side too. And then some of the tests we'll be performing on the battery system in BMS. We'll be testing the individual batteries once they come in a week or two to make sure that the voltages are correct, the discharge looks right, and that the capacity is around what it should be. The BMS circuit will be tested to make sure that if the temperature gets too high, it will indeed trip the relay and turn it off. And then we need to do a ground fault detection test to make sure that if there's a short between the high voltage and low voltage circuits, that it will correctly shut down. And I'm going to hand it over to George.
Before you hand over,
Yeah.
For the lead acid battery, I do not see it very clearly justified how much percentage weight increase and how much percentage volume increase compared to lithium-ion battery.
The volume, as far as the area it takes up, is pretty much around the same. As far as the weight goes, it's a very significant change. It's about 130 pounds versus about 30 pounds.
Almost 5 times.
Yeah, so it's about a 100-pound increase. But
Does that affect other design?
It does affect the suspension, but we've taken that into account, and we may order some more springs that are weight rated for higher amounts. But Stephen can talk about that later in the presentation. And one option we're considering as well, since the reduced cost of the lead acid, would be potentially adding a capacitor bank to maybe implement regenerative braking, because it is an option with the controller that we have. Since it's so late in the design process, it may be hard to implement, but it's still something we're striving to do since the design has become more simple. But we didn't present it in the presentation here because it's not a sure thing yet, whether we're going to put it in.
Personally, I have no objection for lead acid battery. My only concern is that this may only damage it at your conceptual design. If you go to that conclusion, okay, they will give you kind of notes. Well, this is only bad thing I can think of it.
And that's what we were considering doing the capacitors, because it would help the vehicle accelerate a little bit faster, and it would make the system a little bit more complex and interesting than just the lead acid batteries.
I don't know about that part. If you add the capacitor, the workload is much higher, and it will make system more complicated.
This is
I
a
designed it
contingency.
before, because you cannot add a capacitor by yourself. You must add the power electronics interface, okay, and with capacitor, okay. You just do not like a capacitor, like a battery. You just add it there, and you have the BMS, okay. And for the capacitor, you do not just put it there. You must have associated power converters and control to work with them to make the capacitor real function. Otherwise, the capacitor does not, and that is a lot of work, a lot of actual work. I believe.
I mean, this isn't our ideal case. This is a contingency plan of our original design. So it's not up to what we would want it to do, but it's something that we're able to do so the vehicle works.
Now, battery is always a big headache.
Yeah. So I mean, it's not the best case
Yeah.
scenario, but
Yeah, so I
we're
don't
trying to
mind
get
it.
the vehicle to where it can
Right.
run.
Yeah, that
Yeah.
does not affect the other designs significantly.
Yeah.
Just leave as it, the battery itself.
I mean, you won't get extra points for having a high-tech battery, but
Yeah.
you know,
But it's
if the thing runs and is
Yeah.
you know performing okay, then
Yeah.
that's more important.
and that's the biggest thing we're aiming
Yeah.
at. So, but I'll hand it over to George so we can get this presentation, so you guys can get out of here.
All right, I'm George Nimick, and I'll be introducing the mechanical systems for this vehicle. This is our top-level design, and I'll go into more detail about them later, but I'm sure you guys have seen this before in previous presentations. So I'll begin with the first one, with the chassis. And basically, just a review of the design once again. The main purpose of the chassis is to provide a structural barrier between the driver and the components, and any debris or accidents that may occur on the course. And that also provides the ground for an enclosure, since the chassis is tubular, or in our case, tubular. So it would have the incorporation of a body or some aluminum panels to enclose everything. Also, since the chassis basically is basically the foundation for all of the systems, it provides the platform for all the other systems, electrical and mechanical, and basically, like I said, the foundation for where they will interface with all of them and react with one another. So once again, there's two different types of chassis. There's the monocoque and tubular. We chose a tubular, and we went with steel. We could have chosen any or several other different types of metals, but we went with steel. And then also 1018 steel, primarily for the cost, not the strength. And then once again, there's also restrictions, several restrictions placed by SAE in terms of angles, distances, and wall thicknesses for the chassis. And so for wall thicknesses, we use these calculations to try to see where we could increase the outer diameter and reduce the wall thickness in order to reduce weight. We didn't do this in many places. The only place we did this was in the main roll loop and the front roll loop. And the main reason for this was because with thinner wall thickness, it makes it much more difficult to bend without permanently deforming, or I should say without crinkling or creating some sort of deformation, undesirable deformation in the pipe, or in the tube, sorry. And also because 1018 is also has a much lower yield strength than 4130. We did it to help with the strength. And these are the minimum dimensions that are provided by SE for the wall thicknesses of the tubes. And we actually adhere to most of them, like I said, with the exception of the main roll loop and front roll loop. And so one of the main things that to keep in mind while designing the chassis is, again, the space for all the components. And so to help with that, SAE has provided several templates that we must abide by, and these were recreated in solid model form and then placed within the chassis to verify it. And they also have diagrams such as this where we can verify angles and distances. So once again, we started out with basic tubular chassis, primarily to give a certain shape and form that would later change and take shape according to rules and sizing. And then we would later insert these templates to verify space, and then insert a mock of the driver and the components of the vehicle, and then leave us with where we have right now in a solid model. We've also begun designing the body for this so that the IEs can start doing the mold for it, and we can start beginning to fabricate these parts. This is just the nose cone and the skid plate at the moment. I need to design the side pieces that will basically cover the battery containers Yeah.
By the way, did you guys pick up that carbon fiber cloth from Makita? Did you
No,
see
I
that
did not.
email
Thank
from
you
me?
for reminding me. No, I forgot.
Okay. Is that for the nose cone? Is that what that was?
I think that
What
they're
is
going to
it?
be too small. They may be
Oh.
useful for reinforcement. Basically, most of these sheets will have to be very large strips of sheets
Okay.
or strips of carbon fiber that we'll be able to obtain from HPMI. And so, just on a side note, part of the test plan is basically to, I would say, is incorporated in the design feature. So the test plan, I would say, is a solid model, and that is basically what I had shown you in that diagram. Now, in addition to that step or that test plan, I took liberty of taking images of the three-dimensional model and sending it off to the technical inspectors to check for proper triangulation. And it came back with one adjustment that needed to be made, and that was corrected and then resent for verification. And so that has passed. And so then the next step would be the fabrication part. And so we decided to do a jig, and basically the jig, it's probably hard for you or difficult for you guys to see, but there are sketch lines on here, and those dimensions were taken from the solid model. And then these blocks were placed to hold the tubes in the proper positions. And basically this helps to lessen the amount of slop that would normally occur from just tubes sliding around or not being placed at proper angles. And so this would verify that it's being correctly fabricated to the three-dimensional model, and then that all the dimensions will then come from the three-dimensional model and not have to be recalculated to fit. So this is just kind of an example of how it would all fit together. These ones are yet to be fabricated, but you can see that these have already been miter cut and ready for tack welding. So that is the bottom plane that has just been tagged, and then the upper hoops. And I don't unfortunately have a recent picture, but it's also continued further from there. And so then in addition to this, there also needs to be a finite element analysis that analyzes the structural properties of the frame. And unfortunately, this is a very difficult thing to do, especially with the software that we have available to us, because it's very difficult to constrain a vehicle that may not have points to constrain. For instance, the center of gravity may not be an obtainable object, if you will. The frame is hollow in the center, and so there's nothing to constrain it at that center for rotational purposes. And so basically certain assumptions have to be made, and certain impacts have to be observed. And so we chose to do a frontal impact, a rear impact, side impact, full suspension loading, and then single side suspension loading. And like I said, there's many different types of loads that can be done, and none of these are actually, I would say, proper and suitable for actual analysis. But the key thing to get from this is the stress concentrations that would occur in the frame, and that would denote places to place extra members or potentially remove members if something is over strengthened. And so this is just kind of an example. This was for the frontal impact, and it's just kind of a reaction. This is an exaggeration and does not necessarily show exactly how it would yield, but it would basically yield some exaggerated form of this, and this exhibits the stress, and this gives the worst case stress, which is in some 1,000 pounds per square inch. And then it can also, I have also included a video of the displacement, and so it'll measure, and I believe in here for the frontal impact it was quite large, as would be expected. But again, it'll show some sort of deformation. And one of the key things to get from here also is that it'll give you the amount of deformation which which would not be enough to crush the driver, but which would show that it's not enough to crush the driver. And in the exaggerated version, you wouldn't see the two hoops converging and say cutting the driver's neck or something like that. In fact, they're diverging, opening up the cockpit. This is Al Gore. There's several different finite element analysis.
Say again, which one?
Al Gore.
Al Gore.
There's ComSol, SolidWorks, and another one that I can't think of off the top. Mechanical. I chose this one just because I had some experience with it before, and I couldn't get the other ones to work as I had wanted to. I had quite a lot of difficulty trying to constrain things and get the proper stress analysis. And these are a couple others. This was for full suspension loading, and once again, with full suspension, you wouldn't see this sort of deformation from the force of the shock. Instead, this is an exaggerated version, and it's I believe in the displacement it shows that this is a fraction of an inch, it's like 0.003. But rather it tells me that there's a stress concentration here, which is something I would already know because I'm not placing it at a node. Rather this one, the front suspension, is being placed at this node, and you'll see that it has minimal stress concentration. And I'll pass this off to Stephen Kuczynski for suspension.
I'm Stephen Kuczynski. I'm going to run you through the suspension update. So what's to come in this week is going to be a brief overview of going to show you the current progress of the suspension design, go over the deadline and the test plan. So back to the competition constraints. The suspension needs to be fully operational. You need to have usable wheel travel, 2 inches, one for jounce and one for rebound. And ground clearance needs to be at a 1 inch minimum, just static loading with the driver in place. The wheels must be at least 8 inches or more in diameter, and tires we can run dry and wet tires if we have money to buy wet tires. So this suspension design, it's an independent short long arm suspension. It's utilizing a push rod. So basically the upper A arm is shorter than the lower A arm, and the push rod here is what's going to transfer force into the spring dampener setup. This is good for better ride quality, improved handling, and more adjustability than other types of suspensions. And you can also, you have a lot of freedom with your camber angles, and you can reduce wear as well on the tires. So the design method was to first go over the wheelbase and track width of the vehicle, and then design for the front view swing arm and then the side view swing arm. So the suspension layout was a compromise between the chassis and the suspension designs. We kind of went back and forth and said what would work better for me versus what would work better for you. And we also averaged out the wheelbase and the track width from Formula SAE teams that performed very well at their autocross events in the previous years. So the front view swing arm, these are drawings that you can design the front view swing arm in a static case, basically when nothing's moving. And this you can determine your instance center, your roll instance center, and your SVSA length. So basically is you have the tire and you have the chassis, and you select your mounting points, and then from those you project angles. And from projecting the angles, you'll come to a single point, which is your instance center, and the distance from that, from the wheel, is your front view swing arm length. And when those where the instance center contacts the contact patch center line, is going to be the roll instance center. So from all that, we can load this into Atoms and come up with some data. So here we have, this is just a graph of what the other drawing showed for the length of the front view swing arm. And basically from the front view swing arm, you can minimize your camber change, you can reduce the jacking effect, and you can also reduce the scrub. And the main thing is though the camber. You can see here that the angle that we want is around at a static case is what we designed for. And with an inch of jounce of rebound, we're staying negative, and it's not too much of a change, which is ideal for what we're looking for. Moving on to the side view swing arm. In the side view swing arm, we also designed it for the static case where nothing's moving. And from the side view is where you control all of your anti-features. And you do the same thing when you find your instance center locations from projecting the horizontal mounting points of your suspension to the chassis. And from that to the center line of the tire, that is your side view swing arm length. So between the angle and the length is how you come up with the percent of anti-dive that you want. And the percent of anti-dive is basically the amount of force that is carried into the members. So you don't want to have 100% anti-dive because you're more than likely to bend one of the members and break something. And you'll also reduce the amount of pitch that you'll have under braking. So here we are designing for about 30% anti-dive at static case, and it's relatively pretty stable for about 1 inch travel in both directions. So Adam's car is what we're using to run a lot of simulations. It's pretty user friendly. You can do a lot with it. And, Tomas is also using that for steering. So then once we had all that data set up, we went on to the A-arm design. The idea behind the A-arm design is to attach the chassis to the knuckle, but allow for steering clearance. So we have some pretty tight bends, but there shouldn't be anything that we can't actually fabricate. If there does become an issue, we'll have to go back and redesign it slightly. The idea also is to have the endpoints with ternary links in there that you can fully adjust the length slightly, so you can have like a fine tune of your camber angles and whatnot. So deadlines for the suspension, the end of this month really. We need to finish up all the modeling of the A-arms and the knuckles and begin fabrication by the last week of February, hopefully.
Keep in mind there's midterm hardware review scheduled for last week of February, so you should have a plan for what you're going to have to demonstrate in that.
Yeah.
I mean, we don't expect everything to be done by then, but just some interesting subset of the components.
Okay.
I think it'd be
And then
a good point to show off, basically.
Yeah. And as Scott was mentioning about the added weight on the suspension, we initially wanted to go with a lower spring rate than they used previous years, and we already had 2 springs that were at 300 pounds. The previous year used 400-pound springs, so I think we're going to order an additional 300-pound springs, 2 of them, since they're not too expensive. And more than likely, I think we're going to have to stick with the 400-pound springs since we have so much additional weight. But that can also be varied by the amount of preload that you put on the spring too. So we can also adjust that as well when we're fine-tuning the car at the end. So the test plan, there's going to be a 2-stage test plan, fitment and adjustment. Test 1 is going to be the fitment to rules and design. Basically, we need to make sure that we have all the measurements right for all the mounting locations and that they're even and square from the left side of the car to the right side of the car. Otherwise, if they're mounted and they're a little bit crooked and a little off, you're going to have a tendency to pull one way or the other, and it's going to make the car kind of unpredictable when you're turning and going at a high rate of speed. So the procedure of this is to measure as accurate as possible, and then tack weld on the mounting brackets for the suspension, and then measure and make sure nothing has moved a little bit. And then that'll give us our final placement, and once we have that all tacked, we can do a mock assembly of all the members and make sure that there's no binding and everything's going to work the way that we assume that it will be. And then if the mock assembly goes well like it should, then we can just do the final welds on the brackets and be done with it, and then just reassemble everything. The second stage of the test is going to be the setup of the car. It's going to take place basically when the car is all ready, the powertrain's all finished. It's basically to determine the optimal characteristics of the car. So the test procedure is to drive the car and we'll be running tests simultaneously for other things like the braking and stuff. But while we're doing that, we can also be testing the suspension every time. So what we need to do is we need to adjust the toe, caster, camber, spring rates, and tire pressure to make sure that we have the optimal handling adjusted for the car for competition. I'm going to hand it over to Tomas.
All right, my name is Tomas Vachi, and I'm going to give you an update on steering. Okay, the steering design, like I mentioned last time, we're using rack rotating steering. We're just quickly going to go over that. Rotation on the wheel displaces the rack horizontally. The horizontal rack pushes tie rods that push the wheels, and depending on what angle you have set up, you get different steering characteristics. This is proper for application if we can use a dry rack because we don't have like a very heavy vehicle compared to like a production car. where you have things like power steering. Okay, so steering design overview, we also talked about last time we were using reverse Ackerman. Just because the outside tire becomes more loaded in a turn, performance curves show that the peak of the cornering force occurs at higher slip angles as the vertical tire load increases. What this is basically saying is if you have the outside tire loaded more, you want to turn that tire slightly more, like to get a better cornering force peak. Basically, and the reverse Ackerman, if you look at here, it rotates the outside wheel sharper than the inside wheel, which would be the more loaded wheel. So from that, we set up just force balance to see the relative effect that one wheel would experience over the other one. We have the weight, and right here, this is like a mv squared over r, that's central acceleration. These are actually values taken from a sample turn in the competition rulebook for one of the autocross competitions. The calculations are near the end of this presentation, but they yield that the outside. Also, we're taking into account this is a 650-pound car, and I just assumed that the weight was going even between the front and rear. It's just a relative estimate to see the magnitude changes. From that, we got that one wheel weight takes about 180, while the inside takes 145. This tire data right here is for much heavier tires, so you don't see those curves fit in here. But with research we've done, we figured out that the effect of the reverse Ackerman needs to be much smaller than we thought because of the weight being applied on the tires. So we're shooting for about 1 degree of reverse Ackerman, which is very close to parallel steering. So Adam's test results, we tested the steering characteristics using Adam's car software. Last time we talked about how we're going to try to achieve the reverse Ackerman. It was by setting up the linkage so that angle below 90 degrees would develop reverse Ackerman. Under the current steering setup in Adams, it looks something like this. You can see that the angle is sharper, like heavily sharper than 90 degrees. It doesn't necessarily mean that it's not, that's just like a general guide on how to achieve it. We manually kept testing different points until we got results that we were happy with. So model details, it's a little dark, you can't see this. This is the main thing about here, I'm trying to point out the reference frame in relation to the assembly. You can see the steering wheel and the tie rod and the tie rod location. It's mounted below. There's not much on the vertical axis you can see, but the tie rod location is below the hubs. Here are the tire data in inches. It's hard to tell much from this information. What I want to highlight though is that we have the wheel center located in the Y direction, 24 inches. And what it does is it mirrors the other side. That represents the 48-inch track width that we talked about in the front. Additionally, last presentation we talked about the rack that we have in possession from the current team. And you see that it's a 12-inch rack, and after the tie rods attach one at each, it comes out to effectively 14 inches. It's modeled here, the tie rod location is modeled at 7 inches, which models at 14, doubles to 14 when it mirrors around the center. This is just some of the details of how we input the model from the data. The suspension was, I got it from Steven, so I'm fitting our steering system into those suspension hard points. I got the hard points from his data. Here you see, I just wanted to point out how we quantify the amount the rack's moving. We set the parameters to match our rack, and like here you see 4.25 inches of travel total. We split that between the middle halfway because the rack's going to be oriented in the center. And then from that, you can see the Adams simulation. This is like it's a little choppy, but just trying to show you that it doesn't bind. And then I try to come in here and spin it around to give you a better look of where it's located in the chassis. But this right here, I wanted to show you where we're planning on putting it on the actual solid model. Okay, actually, first I want to talk about the simulation results. We have the left wheel in red and the right wheel in blue. And basically, I also want to go over toe out is negatively quantified when the wheel toes out, like away from the car, and positive when it's in. So what I want you to take a look at here is basically, you see this angle is at 23 when this one is at negative 21. The right wheel, which is the blue, starts at a negative angle, basically towed out. When the left wheel is towed in at a positive angle, higher value. than the wheel. Effectively, you're turning the outside wheel, which is more loaded, more than the inside wheel. So yeah, that's what, and these values can be adjusted. We actually, like, you can see differences just by changing the tie rod location. And we can actually affect it, we can actually create different curves also by towing in the wheels initially and towing them out. Also, okay, so here's a picture more of the rack placement where it would be relative to the rack. And the reason that we have the rack tilted is because the column has to transfer the force into that plane, and if you have the rack too low, it becomes difficult to do. The solution is to tilt the rack. Okay, so the test plan ahead, that was a test for the geometry. This is a test plan ahead. Well, for competition requirements, we need to ensure the free plane of the wheel is below 7 degrees. We used last year's team, our setup, and it was verified last year, but we'll just make sure again, like, we'll wiggle the wheel, take on the angle measurement, make sure it's below 7 degrees. For any reason it's not, we'll pretty much make sure it meets all competition requirements. Quick disconnect, that would be taken into account when we do the driver egress test. You have to get out within less than 5 seconds. We have the hex disconnect, we'll make sure it works. You should have no problem. Non-binding, that's partly measured throughout the software, but that software, for example, we don't have like the body drawn on over it. So we have to make sure that when it's actually installed, additionally to what we already think that it won't bind, we need to make sure that it doesn't come in contact. Because if it does come in contact with any rest of the body, we just have to move those steering stops slightly so that they don't, just to ensure that it never binds with the rest of the vehicle.
And have you made sure that none of the steering system components have to go through the same areas of space as the
Suspension?
suspension
Yeah,
or the
yeah,
frame or?
That picture didn't show it too well, but
Yeah.
if you have that, as it's currently set up now,
Yeah.
And that didn't have the correct placement of the shocks, but it had the correct placement of the A-arms. But the shocks would actually it came close to hitting the shock, but it doesn't hit as it sits now. But where the shocks are going to change, they're actually going to increase that spacing. But as it is right now, it doesn't come into contact. It looked like it kind of, when I spun it in there, I wasn't trying to hide anything.
Well, it was just hard to tell because I don't think all the parts of the car were in.
Right, exactly. It doesn't take into account, but yeah, we are taking into account about the fact that it can travel within inside the suspension. I mean, within the rest of the chassis. And also, we'll verify the reverse sacrament. We can do that by measuring each angle, but like I said, it's going to be very close to parallel steering. Test drive, these are the competition rules stating like different characteristics of the autocross event. So we can just try to recreate these as best as we can and just test our vehicle in those conditions. The build progress status, it has not begun, but we're waiting on the final chassis welding to begin installing. Obviously, you can't install the steering without that. Maybe another 2 weeks. Materials, we purchased the rack and pinion, the tie rod, column tubing, the rod ends, column bearing, the removable hex. We still need to fabricate the actual tie rods, cut them down to length, and adjustable end caps, hubs, and the plate that's going to be tilted on. And we need to purchase a U-joint still, but it's a very low demand item. And I'll hand it over to Sam for purchase.
How many more speakers do we have?
Let's
Sam.
Sam one
Okay.
Alright, I'm doing brakes and components, Sam Risberg. Alright, so a typical braking system for most of the cars that you guys probably drive is 2 disc brakes in the front, and depending on how old or expensive your car is, 2 drum brakes or also disc brakes in the rear. In a normal car, you have 1 master cylinder that goes to a proportioning valve. This proportioning valve sends pressure to the front brakes and to the rear brakes. And obviously brake lines, calipers, rotors, which is all the same that we'll be using. In our case, we're actually going to have just 1 brake rotor in the rear with a caliper directly connected to our chassis. So this rotor specifically will be connected directly to our differential. So when our rear wheels are spinning, this will have a caliper that will compress the rotor, and that compression will slow down both rear wheels. It'll slow down the differential, which will in turn slow down the wheels. So this will be unsprung weight, so our rear tires will have less weight on them, which could possibly mean higher acceleration and just less to worry about. Like I was saying, the rotor is directly connected to the differential. You can see the axle coming here, so we're looking at a rear diff from a side view. So there'd be an axle coming out this way, an axle coming out that way, and this rotor would just be connected to the output, and as it compresses, it slows the differential down, which would slow the rear tires down. Like I said, in a normal car we have one master cylinder, but in our case here we have two. So instead of having a proportioning valve, this would be eliminated completely. We would have one master cylinder with a line going to the right and one line going to the left, and then another master cylinder with one line just going to the rear. So instead of having a proportioning valve, we obviously can just control it between the master cylinders. And this is last year's design, where you can see they use this design, and we'll be using it also. Two lines go to the front, one go to the rear. We also want to use a brake bias bar. This will help us pretty much just modify our braking forces either on the fly or just in testing. So if we see that our front tires are doing more braking than the rear, we can adjust it so that the rear does more, and we're not using too much, getting too much heat in the front, using too much brake pads in the front, possibly warping our rotors in the front or rear. And this would be very beneficial in regenerative braking, because we could take away some of the braking that would be in the rear and let the motor take that over, which most likely will be implemented next year, which will help them. But for our purposes, we're just going to use it for remote access to the bias. So with this, in the cockpit, we'll have a rotating valve that will adjust the front and rear brake bias on the fly. If we're driving the car and we start to hit the brakes and we feel like the front is locking up, or we hit the brakes and the rear is starting to lock up, and vice versa, we can adjust on the fly and just see what gives us equal braking. So in competition, pretty much the requirement is the brake system would be dynamically tested and must demonstrate the capability of locking all four wheels and stopping the vehicle in a straight line at the end of an acceleration run specified by the brake inspectors. So we're going to accelerate to a certain probably speed at a certain distance, and we will have to hit the brakes pretty much as hard as we can. All four wheels must lock up, and it must stop in a straight line. So having the brakes in the rear should obviously lock the rear at the same rate, and testing if the left or right front calipers are equivalent would show if the left locks up and the right locks up, then they'd would watch that, and we'd have to test that previous. But that's all we have to worry about.
So they actually want you to burn rubber in that test?
I mean, yeah, they want to see all four wheels locking up. So yeah, they would probably want to see four skid line or two skid lines.
I thought anti-lock brakes were supposed to be a good thing.
Yeah, I mean, if we had the money, maybe we'd put that in too.
Yeah, but then you couldn't pass that test.
Yeah, you're right.
Oh, the brakes won't lock.
That's true. Too sophisticated for that.
So I wanted to go over a little bit of the planning of this project. So currently we are, as the other said, we're in the middle of constructing the chassis. That's currently the bottleneck, and once that's done, then we could get on implementing all these other systems in the vehicle. And right now we're still researching the composite materials that we need, as well as the infusing resin to make the nose cone and floor pan. Probably by next presentation we'll have that all fleshed out, if not already completed.
Is Albrea?
Yeah, they had a separate presentation last week.
And Ryan. So they're both.
Corey's just
You're just sort of representing the IE group.
Yeah, I just wanted our information to get covered. So.
Okay.
This is our current schedule. Extensions from our original schedule are shown in red. You can see that there are quite a few extensions. Basically, the chassis taking a little bit longer has caused everything else to be moved back a little bit. We're still working well inside of our initial buffer range though. So as for right now, it doesn't present too much of a problem. Alright, so as for the ergonomic design of the cockpit and things like that, we went through different body dimensions among the group members and everything, and decided on how we wanted to form certain components in the cockpit and arrange them. So one important criteria was the leg length of our individuals. We have taken a standpoint that we wanted it to be built so that potentially any of the group members could drive the car. So we'd probably average out the leg lengths to decide the position of the throttle and things like that. Maybe add a few inches allowance for compression of the throttle. And that range would be 35 to 40 inches from the seat back. As for the location of the steering wheel, the arm length was important. We didn't want to have the steering wheel placed too close or too far away from the average individual once again. And the seated height had bearings to do with how tall the seat back would be. We designed that for the extreme so that the tallest individual would still be properly covered in the back, and then the location of the head restraint would be determined from this as well. Alright, so this is not only a good design for making the vehicle all around more comfortable and useful, but also for the 5-second egress that other group members were talking about. It seems like it would be a pretty difficult thing to achieve if the cockpit was not designed ergonomically. So we want to make sure that the driver's thighs aren't pinned down, that he could get it out of the cockpit easily. Alright, so now for the budget and purchasing. Our original budget of $9,000 has gone to these following purchases on the registration, tubing, and brakes, batteries. Batteries were the easiest one to go through. So our current budget we're working with right now is about $5,000.
And I'd like to point out for the batteries, one of the reasons we have so much more in our remaining balance is because the batteries were about $600 less since we went to lead acid. And then a lot of the components on the vehicle we were able to reuse, so there wasn't a need to buy a lot of the parts from that. And plus we got that extra donation from Cummins about a month ago, which greatly increased it. It was about a $2,000 donation, so that made the budget go up a little bit.
So what are your remaining major expenses?
We're thinking that we could allow some for travel, as well as we'd have the option now to look into certain upgrades like the wet tires if we want to get the rain certification, which I'll cover in a little bit.
So gosh, you've trimmed your costs quite a bit from the $30,000 earlier
Yeah, the
estimate.
tubing was reduced by almost $1,000. So it went so much.
Right. Plus you went from 4 wheels to 2 wheels and
4 motors to 1 motor.
4 motors to 1 motor, right?
And we already had 2.
Then you already had the motor. Okay. Well,
So we may kind of look at things that wouldn't take too much extra time to design and implement.
you're becoming experts at frugality, I'd say. So, forced to become experts at frugality. Okay, so is that it?
The
inspection.
That's actually the
Um,
larger amount of what I.
Oh, really? We're running over time now. I have another group that's waiting probably outside. So let me check and see if they're here. If they're not here, you can.
I think I saw one of them was out there.
Can you just? Okay. This one has been running a little bit over. Can how long is this remaining part?
5 minutes.
5 minutes? Are you guys okay to wait 5 minutes? I appreciate it. Hey, sorry, these things always seem to run over. Sorry. Okay, just quickly go through
Yeah,
this.
I'll
Okay.
rush through this.
We had
So,
if you wanted to get there.
What's that?
Yeah.
So inspection of design. Purchases, this is, so we went through an original inspection of the designs of the vehicle at this portion, looking through the competition rules comprehensively through every single one. And out of all of those, we found little purchases here and there that we'd have to make. Most of them are safety equipment, stuff like that. And then we found 11 designs that needed to be kind of tied down more. You've already seen that some designs are still in the works. And 3 of our completed designs were found to have disagreements with the criteria from the competition. This inspection was done 2 weeks ago, so some of these things have been fixed already. But these are some of the purchases we found. As you can see, most of them like fire extinguisher, some free big red buttons from the competition, stuff like that, driver suit, kind of small stuff. Some could be got at a hardware store. And then as far as the different systems we had to work on, there are some that may have not been completed because they're waiting on others to be completed and they can kind of be worked around, like where we're going to snake around all the high voltage wires and everything. We could probably arrange that around the completed chassis and everything. So these aren't as pressing, but then these ones are ones that we could be working on now and kind of getting a little bit more thorough of an idea for. If you had any questions on any of these, then you could ask me, but I know that's just a summary of it. But, so basically we know that our purchases need to be made promptly and we need to correct and finalize this thing. We're planning on having 2 more inspections. One in the middle of our construction of the majority of the components. We'll make sure that the initial inspection, the notings from that are being followed and worked on, as well as different protocols for construction. A lot of them are common sense, like leaving a certain amount of threads out of the nut and things like that. But we'll kind of be looking around, making sure that's being constructed in a good way. And then after everything's done, when we move into testing, we'll also cover comprehensively all the rules again, make sure we're not going to get disqualified and sent home from the competition. Okay, so once we finish the chassis, we'll be able to get through it right now.
Okay, great. Are there any burning questions from the committee? Because if not, we probably just need to end it here.
No, you can go.
All right. Thanks, guys. Good work. All right. Oh, sorry.